Good afternoon, all of you, and I welcome you to the third day's lecture. Today's first lecture and fourth in the series is on The Sun, Our Star by Professor Arnab Roy Chowdhury, Indian Institute of Science, Bangalore. And moderator of today's lecture, first lecture, is Professor Deepankar Banerjee. He is currently the director of Aryabhatta Research Institute of Observational Sciences at Nainital. His research interest is in the theoretical study of solar magnetohydrodynamics, wave propagation in stratified atmospheres, observations of chromospheric and coronal oscillations, density and temperature diagnostics in solar atmosphere. Over to Professor Deepankar.
Thank you very much, Dr. Praveen Kumar. It's actually an honor for me to introduce today's speaker, Professor Arnab Roy Chowdhury. Fondly, we call him Arnabda. Very briefly, Arnabda did his BSc from Presidency College, Kolkata, way back in 1978. And then he did his master from Indian Institute of Technology, IIT Kanpur. And after that, he went to University of Chicago for his PhD studies. And he was supervised by a very famous physicist and solar physicist, Eugene Parker. Probably some of you are aware of the solar wind, which was first named by Eugene Parker, and also now the NASA has named its famous satellite as Parker Solar Probe. So after completing his PhD from University of Chicago, Professor Roy Chowdhury returned back to India and joined as a faculty in Indian Institute of Science, Physics Department. And since then, he's been continuing his work at Indian Institute of Science, and he has been pivotal to initiate a joint astronomy program. And some of us are a product of that joint astronomy program. It has been a privilege for some of us to attend Professor Roy Chowdhury's classes. And also he has contributed to, phenomenal books more on the theoretical aspects of the sun and the stars, and also about the cosmos, and also a popular book, Nature's Third Eye, a story of sunspots. So with that brief introduction, I would request Professor Roy Chowdhury to give today's lecture. And for friends who are joined online, you can pose your questions in the chat box. And at the end of the lecture of Professor Roy Chowdhury, I will take up those selected questions and request Professor Roy Chowdhury for the responses. It's all over to you, Professor Roy Chowdhury.
So thank you, Deepankar, for the very kind introduction, and special thanks to Dr. Praveen Kumar and other organizers of STAR 2024 for inviting me to this lecture. This title of my lecture, The Sun, Our Star, was chosen by the organizers and not by me. So this title might have convey the impression that this lecture is going to be a very comprehensive introduction to all aspects of the sun. But as I started preparing the lecture, I realized that solar physics, the study of the sun, has become such a vast subject that it is completely impossible for anybody to give a comprehensive introduction to this subject in half an hour. So I shall mostly focus on one aspect of the subject, solar activity. In a few minutes, I am going to explain what that is, and you will see that solar activity has very intimate connection with space science. But at the outset, I should also point out that there are many other important topics in solar physics which I would not be able to cover in this talk. So for example, some of you may know that Ray Davis won a Nobel Prize in physics for the discovery of neutrinos from the sun. So certainly I shall not have time to discuss solar neutrinos and some other important topics. So let us come to solar activity. So what is it? So according to elementary textbooks of astrophysics, a star is a spherically symmetric hot ball of gas inside which nuclear reactions are taking place. Now, there are many phenomena in the sun which makes it much more complicated and intriguing than a simple spherically symmetric hot ball of gas. So such phenomena are collectively called solar activity. So let me begin by giving you, recounting some examples of solar activity. So the type of solar activity which has been studied for the longest time happen to be the sunspots. So these are dark regions on the solar surface, and some of the largest sunspots can be larger than the Earth. So here I show a photograph in which you see two large sunspots side by side, and the size of the Earth is indicated here for comparison. And in a few minutes, I shall discuss why it is you very frequently see two large sunspots side by side, or why sunspots appear in pairs. So in 1844, Schwabe discovered that sunspots have a 11-year cycle. So here I show a plot of sunspot number against time for the last 400 years or so. So you can clearly see this 11-year periodicity, but you also see that this is not a very regular cycle. It has lots of irregularities. So the next manifestation of solar activity I want to mention is the solar corona. This temperature of the surface of the sun is a little less than 6,000 degrees Kelvin, but some regions of the corona can be as hot as 2 million degrees. And if you look at this image of the corona taken during a total solar eclipse, you can see that it is far from being spherically symmetric. Now, according to simple stellar structure models, the temperature and density of the sun near the solar surface would go to zero, and beyond the surface, there would be nothing more. So why is the solar corona there, and what causes its very high temperature? So lastly, another important manifestation of solar activity is the solar flares. These are explosions which typically occur above sunspots. So here I show a video of a solar flare. So the energy released in a major flare can be of the order of 10 to the power 26 joules. So for comparison, remember that the atom bomb which destroyed Hiroshima had an energy of 10 to the power 14 joules. And these are unbelievably energetic events which even affect our lives, even though we are so far away. So on March 13, 1989, about 6 million people in Quebec, Eastern Canada, were without electricity for 8 hours. And apparently this power blackout was caused by a large flare which was seen by solar astronomers 3 days earlier. So these effects of the solar disturbances are maximal near a geomagnetic pole. And since one geomagnetic pole is very close to Eastern Canada, that is one particularly vulnerable region. So when solar astronomers first started studying solar activity, it was initially thought that that different manifestations of solar activity are completely unrelated phenomena. Maybe the people thought that, astronomers thought that solar corona has nothing to do with sunspots. So it was mainly during the second half of the 20th century when solar astronomers realized that there is a sort of underlying unity behind all these different kinds of solar activity. Basically, all these types of solar activity are caused by one entity, the magnetic field of the sun. So the study of solar magnetic field began in the year 1908 when Hale found evidence for Zeeman splitting in the spectrum of a large sunspot, and from which he concluded that sunspots are regions of strong magnetic field of about 0.3 Tesla, which is approximately 5,000 times the magnetic field near the geomagnetic pole. And within the next few decades, astronomers realized that magnetic fields are ubiquitous in the astronomical universe. So most stars, planets, and galaxies have magnetic fields. And Hale et al. Also made another very important discovery a few years later. I already pointed out that often we see two large sunspots side by side. So Hale et al. Found that in such sunspot pairs, the two sunspots usually have opposite polarities. If one of them has positive magnetic polarity, the other has negative polarity. So the most plausible explanation for that is that there must be some strand of magnetic field underneath the sun's surface, which is poking its nose to the surface in this kind of fashion. So if these two intersections with the solar surface become the two sunspots, then in one sunspot you have magnetic field lines coming out, making it a positive polarity sunspot. And in the other sunspot, you have magnetic field lines going down, making it a negative polarity sunspot. And if this idea is correct, then the solar corona would be full of such magnetic loops above the sunspot pairs. And we now know that this is the case. So within the last few years, solar astronomers have developed ingenious techniques for mapping these magnetic loops in the corona. And here you can see a beautiful image of magnetic loops in the solar corona. And now I show you something which I find absolutely fascinating, a magnetogram map of the solar disk. A magnetogram measures the magnetic field at every point of the solar surface. If the magnetic field is positive, then white color is put. If it is negative, then black color is put. And if it is too weak, then gray color. So you will see here that there are many places where you see a white patch and a black patch side by side. So this means that there are two sunspots here. One of them has positive polarity and the other negative polarity. And you also may notice that in the northern hemisphere, you have a white patch or the positive polarity sunspot on the right side and the black patch or the negative polarity sunspot on the left side. And in the southern hemisphere, it is opposite, this with black on the right and white on the left. And things remain like this for one cycle of 11 years. So if you were to produce a magnetogram map 11 years later, then we'll find that in the northern hemisphere, black has come to the right and white has gone to the left. And in the southern hemisphere also a similar reversal. So you actually have to wait for 22 years if you want the magnetic field to come back to its original configuration. And if you look at this distribution of magnetic fields inside sunspot pairs, you can almost get a feeling that there must be a magnetic field structure like this underneath the sun's surface. So this magnetic field components, which we call toroidal magnetic field, which is in opposite directions in the two hemispheres. And if these parts of this toroidal field were to float up to the surface, exactly as indicated in this image, then you can easily convince yourself that if parts float up to the surface, then you would get a sort of a distribution of magnetic fields in bipolar sunspot, exactly as you see in this magnetogram map. So now the question is, how can we theoretically understand this kind of magnetic structures and how do they arise? So coming to the theory, I would first say a few words about the plasma state, the fourth state of matter. So Meghnad Shah studied how on increasing the temperature of a gas, its atoms gets broken into positively charged ions and negatively charged electrons, and eventually the plasma, eventually the gas gets converted into a plasma. So because of the electrical attraction between positive and negative charges, they remain well mixed. So if you consider a small volume of the plasma which has sufficient number of charged particles, you will find that positive charge nearly balances negative charge. So you may wonder, then does the plasma behave like a neutral gas? So no, the difference becomes clear if you put an electric field. So a neutral gas like the air is a bad conductor of electricity, but in a plasma, an electric field makes ions move in the direction of the electric field and electrons move in the opposite direction, giving rise to a large current. And you know that the currents give rise to magnetic fields. So you can have complicated interactions between the plasma and the magnetic field. So how can you study such interaction? So even though air is made up of molecules, you can treat the air as a continuum for many problems of air flow. Similarly, many problems of solar activity can be studied by regarding this plasma as a continuum. And then you can study the interaction between the plasma and the magnetic fields by combining electromagnetism and fluid mechanics. And this combination goes by the tongue-twisting name magnetohydrodynamics, abbreviated as MHD. So I don't have time to get into a detailed discussion about the basics of MHD, but let me just point out that there is a very important dimensionless number in this field, is magnetic Reynolds number. So here I point out how it is defined, but let us not get into those details. Just note that magnetic Reynolds number is directly proportional to L, where L is the size of the system. So this means that the larger the system, the bigger is the magnetic Reynolds number. So this magnetic Reynolds number turns out to be much smaller than 1 for laboratory plasmas and much larger than 1 for astrophysical plasmas, and it follows from MHD equations that the plasma behaves very differently in these two limits. And this limit of a large magnetic Reynolds number, Alfvén proved a very famous theorem in 1942, Alfvén's theorem of flux freezing, that magnetic field is frozen in the plasma and moves with it. So what exactly do I mean by that? So let me illustrate by a thought experiment. Suppose you have a block of plasma between the pole pieces of a magnet, and suppose this block is moved sideways, then what happens? So in the case of low magnetic Reynolds number, nothing special happens. The plasma blob is moved here and the magnetic field remains back as it was. But in the case of a high magnetic Reynolds number case, you know that because of Alfvén's theorem of flux freezing, the magnetic field has to remain frozen in the plasma blob. So when the plasma blob is moved here, the magnetic field has to take up this kind of configuration. So some of the most interesting results of MHD are for this case of high magnetic Reynolds number situation, which cannot be tested in a terrestrial laboratory. So one often says that the sun is the best laboratory for high magnetic Reynolds number MHD, and you can MHD to study solar activity, and that subject is called solar MHD. And I would say that there are three very key ideas of solar MHD. So firstly, this magnetic field is frozen in the plasma, which I already discussed. And the other two ideas are not unique to MHD, but even you might have encountered these ideas even in your electromagnetic theory courses, that magnetic field has a pressure B squared over 2 mu, and a magnetic field has a tension along field lines, so that a magnetic field behaves like a stretched rubber band. So now I want to show how, by using these three key ideas, many aspects of sunspots can be explained. Now the sun also rotates around its rotation axis like the Earth, in about 27 days. But unlike the Earth, which rotates like a solid body, the Sun has what is called a differential rotation, which means that in different regions of the Sun, the angular velocity can be quite different. So the angular velocity is largest near the equatorial region. Now think that there is a magnetic field line like this, like a field line of the geomagnetic field. The Sun is also known to have such magnetic fields. So because of Alfvén's theorem of flux freezing, the faster moving plasma near the equator would drag this magnetic field line. So after some time, magnetic field line would look like this. And you would see that you now have a strong toroidal field with opposite, which is in opposite directions in the two hemispheres. So if the parts of this toroidal field were to float up to the surface, they would produce bipolar sunspots with oppositely directed polarities in the two hemispheres, as you saw in the magnetogram map. But why should parts of this toroidal field float to the surface? Well, consider a region where there is a sort of a strong magnetic field. So that is, sorry, I seem to have lost the presentation.
You can open it again.
Yeah. So let's see that. So can you see it now?
Yes, it's back. Fine.
Okay. So you consider a region with a strong magnetic field, a magnetic flux tube. So inside it, the magnetic field would have a pressure. And since you expect a pressure balance between inside and outside, you expect that the gas pressure outside should be equal to the gas pressure inside plus magnetic pressure. And that implies that this gas pressure inside should be less than gas pressure outside. And that implies that, the density inside may also be less than density outside. And then this flux tube would be buoyant. This is called magnetic buoyancy, which was first pointed out by Parker in 1955. So because of this magnetic buoyancy, this magnetic field, this toroidal magnetic field inside the Sun may become buoyant and rise to the solar surface to produce these bipolar sunspots. So largely, why the sunspots are dark? It turns out that heat is transported by convection just below the solar surface. So you see convection taking place surrounding a sunspot, and because of the magnetic tension of the magnetic field inside the sunspot, that opposes the random motions associated with convection, and convection is suppressed to a large extent inside a sunspot. So heat transport is less efficient, and that's why sunspots appear darker. So now you have some idea how, by combining these ideas of flux freezing, magnetic pressure, and magnetic tension, we can explain various aspects of sunspots. Now we come to a very key question. Why does the Sun have magnetic fields at all? And what causes the 11-year sunspot cycle, which is presumably a magnetic cycle? And as I pointed out, that most other astronomical objects also have magnetic fields. The branch of MHD in which we try to understand how magnetic fields are generated in astronomical objects, so that branch is called dynamo theory. So since I have worked on dynamo theory for many years, I would have been happy to give a systematic introduction to dynamo theory. But I realized that only if I give a 1-hour lecture devoted completely to dynamo theory, then only I can give a sort of an introduction to dynamo theory. So since that is not possible here, I shall just make a few comments about dynamo theory. So in 1955, Parker derived the dynamo equation, the basic equation of this subject, and also gave a model of the 11-year sunspot cycle. So even now, when we try to model, try to understand how magnetic field is generated in an astronomical object, we start with the basic ideas which Parker gave in this paper. But within a few years, it was realized that Parker's model of the 11-year sunspot cycle, that was not a very complete or satisfactory model, because that was based on the very limited amount of observational data available at that time. So as more and more observational data started coming, it was realized that a more complete and improved model was needed. So from the 1990s, a model started being developed called the flux transport dynamo model. So our group at IIRS has contributed to the development of this flux transport dynamo model. And these organizers told us speakers that we should highlight any work done in India, any important work done in India. And of course, I do not want to make any comment whether our work was important or not. That should be judged by others. But I can just mention that special recognition for our work came about 2 years ago when I became the second Indian to receive the Chandrasekhar Prize of Plasma Physics after Professor P.K. Kaur, who received this prize about a decade earlier. So as the citation of this prize says that it was for the key role in developing this flux transport solar dynamo model of the 11-year sunspot cycle. And I should mention that I was lucky to have a succession of extremely brilliant PhD students whom I have listed here. And my work on this flux transport dynamo model was done with them. So the prize might have been given to me alone, but this is a collective this is a recognition of the collective work that all of us did jointly. So anyway, after giving this introduction to sunspots and dynamo theory, let us move to the corona now. And yeah, so I'm again losing it. Let's see, I don't know why I'm losing it again and again. So you can see the screen now.
Yes, Arnold, I'd seen, but I think, yeah, your office has some problem, Microsoft Office. Yeah,
Yeah, I don't know. It was just working and then
yeah, that slide.
okay. So as I already pointed out that, oh no, it's again giving this problem. Yeah, I don't know. It was working completely fine.
Yeah, you can go back to the presentation mode.
Yeah. I don't know why. Okay, hopefully now it will work. So as I already pointed out that that the corona has regions of corona have temperature of the order of millions of degrees, and from a simple application of Wien's law of black body radiation, you can conclude that such high temperature gas would emit in X-rays and extreme ultraviolet. And the upper layers of our atmosphere happen to be opaque to such radiation. So to detect such radiation from the corona, you have to put instruments for detecting X-rays or extreme ultraviolet in space missions and send them above the Earth's atmosphere. And that is routinely done in the last few decades. So here you see images of the solar corona in the extreme ultraviolet taken from space. So on the left side, you see this image of the rotating sun taken during sunspot minimum, and here it taken during sunspot maximum. So you see that the solar corona appears quite different at different phases of the sunspot cycle. And at the sunspot maximum, you see lots of loops. So these are nothing but these magnetic loops above the sunspot pairs, and these are the brightest region, indicating that whatever be the mechanism for producing heat in the corona, that mechanism is maximally operative within the within this coronal loops. So what could be this mechanism? So magnetic fields in the coronal loops imply that there are also currents. And you know that when a current flows through a metal wire, it gets heated. So could the corona be heated because of the ohmic heating produced by the current? And when order of magnitude estimates were made, it was realized that if currents flow through very large regions of the corona, then too little heat would be produced. So only if we can somehow force the currents to flow through the narrow regions of the corona, then only sufficient heat could be produced. So Parker gave a scenario how that may happen. So you may normally think that the magnetic field in a coronal loop would look like this. But underneath this coronal loop, you have you have vigorous convection, so that will disturb this magnetic field, so that it may have a sort of a tangled appearance. And Parker showed that in such a situation, the current is forced to flow through very narrow regions, and that may produce the large amount of heat in the coronal loop. So after this discussion of the loop, coronal loop, let me come to solar flares. Several scientists developed the models of magnetic, what is called magnetic reconnection, to explain solar flares. So suppose you have a region of plasma on the two sides of which the magnetic field is in opposite direction. If you apply Ampere's law, then you can easily conclude that current density would be quite high in this region. And since ohmic heating goes as J square, so that means that there will be quite a lot of heating produced. So, and you now know that the corona is full of magnetic fields. So suppose some new magnetic flux system emerges from underneath the surface in a region where there is an underlying magnetic field which has a different direction. So at this interface between the old flux system and a new flux system, we would have magnetic fields in different directions on the two sides. So there may be a huge region in where this sort of a magnetic reconnection takes place, causing a large explosion. And when you have these kinds of explosions, often that throws away large chunks of plasma, as you see here. And oh, again,
File which
so I shall not open this movie file. So you saw that it throws away large chunks of the plasma. But maybe I shall open, but what happens to them? So they move through the corona in the form of what are called coronal mass ejections, or CMEs. So let me try if I can open it here. Yeah, it's working now. Oh no, it's again causing this problem. Don't know why this is happening again and again. I think it's the last movie. Let me try to. Okay, so now it's working. So you can see this coronal mass ejections moving away. So this image is taken with a coronagraph, within which you produce an artificial eclipse by blocking the central region of the by blocking the solar disk with an occulter, so that you can see the corona. And if you look at these CMEs, then you get a feeling that there is some kind of an outward flow from the sun, which is carrying away these CMEs. And what is this outward flow? So you know that the Earth's atmosphere is held to the Earth by the Earth's gravitational field. So you may try to imagine what happens if suddenly the temperature of the Earth's atmosphere becomes much higher, then the Earth's gravitational field will find it more difficult to hold on to it, and the atmosphere will extend quite a bit against the Earth's gravitational field. So in 1958, Parker realized that the solar corona is so hot that sun's gravitational field would be unable to keep this hot corona confined. So he realized that he suggested that the outer parts of the hot corona would expand in the form of a plasma outflow, which he called solar wind. So at that time, most of the scientists of that era thought that it is quite an absurd idea. But within some 3 or 4 years, solar wind was detected by in situ measurement from space missions, and the density and velocity of the solar wind near the Earth's orbit were found to be in conformity with Parker's prediction. So that is regarded as a sort of a big triumph of theoretical solar physics. And you know that the light takes about 8 minutes to travel from the sun to the earth. Whereas the solar wind takes about 3 to 4 days to cover the sun-earth distance, and these debris of the solar disturbances are carried in the solar wind. That's why after a major solar disturbance, the earth is affected typically 3 or 4 days later. And the solar wind impinges on the Earth's atmosphere and makes it lopsided like this. And I believe some of the other speakers will discuss the solar wind magnetosphere interaction. So without getting into it, let me advertise a little bit about my popular science book, Nature's Third Cycle, where I have given an introduction to solar physics and also have given non-technical introduction to the subject of dynamo theory, which I did not have time to discuss at all in this lecture. So if you find this subject interesting, you may want to look at this book. And since this book was published in Oxford University Press, UK, maybe the hard copies of the book are maybe somewhat expensive for Indians, but presumably the Kindle edition is not unaffordable. And so now I come to my last slide with this one particular comment. So a particular academic field has a kind of intellectual appeal if we find that different phenomena studied in that field have a kind of a unifying thread connecting these different phenomena. And that is certainly the case in the study of solar activity. So firstly, to begin with, you have the dynamo process, which produces magnetic fields in the sun. And then due to magnetic buoyancy, the magnetic fields rise to the surface and produces sunspots. And above the sunspots, you have these currents in the loops, which produces the hot corona. And this hot corona drives the solar wind. And one unique feature of this field was that it was one individual, Professor Eugene Newman Parker, who essentially discovered all the crucial links in this chain of causes and effects. So he gave the formulated dynamo theory. He gave the idea of magnetic buoyancy, and he also pointed out how the currents in the loops would cause the hot corona, and he predicted the solar wind. So as Dipankar pointed out, I had the privilege of doing my PhD under his supervision at the University of Chicago. And here is the building laboratory for astrophysics and space research where we all worked. So this corner room was Professor Parker's office. And this corner room here was Professor Subramaniam Chandrasekhar's office. And my office was here next to Professor Parker's office. And since this upper part of this slide nicely summarizes these various ideas which I discovered, phenomena and ideas which I discussed in my talk, so I have not prepared any separate summary slide. So I leave this summary in this form before you and stop here. So thank you for your attention.
Thank you very much, Professor Raichaudhuri Arnabda, for a very nice overview of the basic phenomena happening on the sun and the solar atmosphere. Yeah, I would request the moderators to pose their questions in the chat box so that I can moderate those questions. Yeah, I am still waiting for some questions to pop up in the chat box. Meanwhile, briefly, Professor Raichaudhuri, would you like to say anything more about, particularly Professor Parker and your interaction with him?
Well, he expected his students also to work on their own and write their own paper. So certainly that was with very minimal guidance. So certainly that was not very easy, and initially it was a very tough time. But it was an extraordinary experience to work in this environment with stalwarts like Professor Parker and Professor Chandrasekhar, whom I could see every day.
Yeah, that's right. So for the youngsters, it's a sort of learning lesson how independently you people worked and did a lot of innovative work. Yeah, Praveen ji, you have to just tell me because I don't see any, any notes yet in the chat box. So,
Yeah,
is there any other
actually,
platform?
Yeah, it is available in that chat box. Perhaps I can read out few questions.
Yeah, please do it because the chat box which I see do not have any. Yeah.
Okay.
So please go ahead.
The question, actually one question. Sir, why do the polarities of sunspots changes almost periodically in 11 years?
Well, I said that explanation for that comes from dynamo theory, and I did not have time. So as I said that if I were given a 1-hour lecture on dynamo theory, I could have answered that question, but that requires quite a lot of explaining. So I would ask students interested in this subject to look at my popular science book, where I have discussed this question at length in non-technical language.
Okay, so I could see the questions now. Yeah, there is another question by Adhurut R. Govind. How sunspots affect Earth?
Well, sunspots do not directly affect us, but in the magnetic field above the sunspot, that may be causing the solar flares. So when there are more sunspots, there are more solar flares, and debris of the solar flares, they are could be carried by the solar wind to the Earth if the Earth is in a favorable or unfavorable location. So that's how this effects of this solar activity are communicated to the Earth.
Okay, so the question from Prince Kumar Singh is asking: is it possible that our sun dissolves in black hole?
No, for a star to become a black hole, its mass has to be larger than the Schwarzschild mass, which is it has mass has to be larger than 1.44 solar masses. So the sun will eventually become a white dwarf and not a black hole.
Yeah, thank you. Avijit Ghosal is asking, what is magnetic tension and how can it suppress convection?
Well, magnetic tension is something about which if you look at your, I think, advanced textbooks of electromagnetic theory, you will find a discussion of that. I think Jackson's book or what are the Griffith's book. I think all these books have a discussion of magnetic tension. So you can look up this book. So books. So because of this tension, the magnetic field behaves like a stretched rubber band. So if you try to disturb the stretched rubber band, it resists this disturbance. And in order for convection to take place, you need to have lots of random motions. And because of the magnetic tension, this magnetic field opposes these kinds of random motions, and that's how convection gets suppressed inside sunspots.
Thank you. Mohit Desai is asking, do sunflares coming from sunspots can generate any harm to Earth? So it's related to earlier question. Maybe you can.
Well,
elaborate.
certainly, I pointed out that there is a large blackout in Canada, and also about the direct sort of harm that certainly it can be more harmful to astronomers in space. So unless proper precautions are taken, so astronomers in space or even in passengers in high altitude flights, they are there can be damages caused to their bodies by particles and radiation coming from solar flares. And certainly, if a large solar flare takes place, it has been estimated that a very large solar flare can by causing a big disruption to various things can cause a loss to world economy to the tune of billions of dollars.
Thank you. Prince Kumar Singh is asking, how do scientists calculate the current age of sun?
Current age of the sun.
Yeah.
Okay, so that is an interesting question. So even though this density of the sun falls off gradually, but it turns out that what we call the scale height, the radial distance within which the density value of the density falls very rapidly. So that scale height becomes particularly short near the surface of the sun. So that's why it seems to us that the surface of the sun is reasonably sharp, even though from our distance the surface of the sun appears reasonably sharp. But certainly the surface of the sun is not very sharp. It's if we could go near the sun, we would see that the surface of the sun density falls over something like a few hundred kilometers. But from a distance but since the sun's radius is of the order 700,000 kilometers, so 1,000 kilometers is negligible to that over which the density falls off. So that's why the sun's surface appears quite sharp to us.
No, I think he's asking for the age, means the lifetime, the age of the sun.
Oh, age. Oh, not EDG.
Yeah, not EG,
so
but AGE. Right.
Okay,
right.
okay. So the sun's life has been estimated to be something like 4.5 billion years, and astronomers estimate that. So as the sun shines, because hydrogen is getting converted to helium, and according to current estimate, the sun is in middle age. So sun has enough hydrogen to run for perhaps about 5 billion years more, after which it will become a white dwarf.
Okay. Mr. Rakendu is asking, as the time passes, the sunspots are increasing. Is there any significance that connected with our existence?
No, I think as I showed in the plot of the very beginning plot, that that sunspot cycle is fairly irregular, and there have been these kinds of era, that 17th century called Maunder minima, when for something like 80, 90 years, sunspots were not seen at all. But apart from these kinds of irregularities, we find that the number of sunspots increases or decreases with this 11-year periodicity. Of course, we have no direct information of how things were in the prehistoric times, but there are ways of finding out the history of solar activity till about 10 or 11,000 years. So it seems that apart from these some large irregularities, the nature of the solar cycle for at least about 10 or 11,000 years remained more or less as we have it now.
Yeah. So Rudravo Banerjee is asking why solar wind occurs. You have explained it in your seminar, but yeah, maybe you can repeat.
Okay, so that is basically an atmosphere of some gravitating body like the Earth is kept attached to it only if the gravitational field is able to hold it, and if the atmosphere becomes hotter and hotter, then it becomes more and more difficult for the gravitational field to hold it. And Parker realized that the corona is so hot that the sun's gravitational field would not be able to hold on to it, and that's why Parker his mathematical calculations showed that the outer regions of the corona would expand in the form of a plasma outflow. So that's how he solved the mathematical equations of hydrodynamics and for the sun, for the solar situation, and found out this result. And he was able to calculate how the density and velocity of the solar wind would vary with distance from the sun, and which were later confirmed from space missions.
Yeah, Professor Raichaudhuri, you have already mentioned about dynamo theory was not. I mean, it was not possible for you to give a full details, but I see a lot of interest on that. So Kanupia again asking, sir, can you give us some more insights on flux transport dynamo model? So we have maybe a few more minutes, maybe a couple of minutes.
This may be the last question.
Yes, yes.
Okay. Yeah.
Right. You can take your time too. Yeah.
Okay, I think giving a very short introduction to flux transport dynamo model is somewhat complicated. So let me mention that that within the last 50 years or so, it has been found that that there is a continuous plasma flow at the surface of the sun, which is plasma continuously flows from the equator to the pole. The flow velocity is something like 20 meters per second, which is comparable to the speed with which a car moves on a highway. So certainly, so what will so when Parker was developing his initial model of the sunspot cycle, so at that time nobody knew about this meridional circulation. So after this meridional circulation became after it was discovered, it became clear that the meridional circulation would play a very important role in this solar cycle. So this model, flux transport dynamo model, which our group and some other groups developed, in these models, this meridional circulation plays a very important role. So that is one aspect. So there are many other aspects of the flux transport dynamo model based on data results which are not available during Parker's time. So I don't have time to explain those things. So again, I would say that in my popular science book, I have given a non-technical introduction to this flux transport dynamo model in a step-by-step manner. So students who are interested may look at my popular science book.
Thank you very much, Professor Raichudhary, for giving such a wonderful lecture and also answering very patiently all the questions. I will request Dr. Praveen Kumar to take it forward from here.
Yeah. Thank you, Professor Arnab, for a very interesting as well as very informative lecture. I would also like to thank Professor Deepankar Banerjee for moderating very nicely this session. Thank you, both of you.
Oh,
thank you very much.
Okay.
Geophysical Research Laboratory, Hyderabad. He is a senior scientist, and the moderator of this lecture is Mr. Abhishek Misra. He is currently working as a CSIR Senior Research Fellow at National Geophysical Research Laboratory, Hyderabad, same institute. So he studies the tectonic history and seismicity of the moon at a global scale as his PhD project under the supervision of Dr. Senthil Kumar. His work provided a first seismic hazard map of the south polar region of the moon for the benefit of NASA's Artemis mission. Over to Mr. Abhishek.
Thank you, sir. Good afternoon to everyone. So I am here to introduce the speaker of today's talk, Dr. P. Senthil Kumar. He received his graduation and post-graduation degree in geology from Madras University and a PhD degree from NGRI and Osmania University, Hyderabad. He is currently a principal scientist in CSIR National Geophysical Research Institute, Hyderabad, and associate professor. His research area includes the geology of Earth, Moon, Mars, and Venus. He founded the newly formed Planetary Science Division in CSIR NGRI, Hyderabad. He studies the meteorite impact craters to understand the impact deformation and fragmentation of the target rocks. His recent works on seismicity and tectonics of Mars and Moon are well recognized in the international scientific community. He elucidates the geologic history of planetary surfaces through detailed geological mapping using various orbiter mission data. His geological map of an area from the southern hemisphere of Venus is jointly published by NASA and USGS. He contributed to the science analysis of orbiter data obtained from Chandrayaan 1 and 2 missions by Indian Space Research Organization. He has published around 50 research papers, both in national and international journals. Prior to his entry to planetary science, he studied the Precambrian geology and crustal thermal structure of Indian silt. He has been a recipient of I.G. Krishnan Gold Medal, INSA Young Scientist Medal, and the Associate of Indian Academy of Sciences, in addition to other professional recognitions. So I'll welcome Dr. Kumar for this talk titled as Earth, its origin and its evolution. And also I request the participants to put their questions in the chat box along with their names and email, so that if we cannot address them in this session, we can reply back to their email along with their questions and the answers. Thank you. Over to you, sir.
Thank you, Abhishek, for a nice introduction. Now I load the slides. Do you see, Abhishek?
Yes, sir. It is visible, sir. Yes.
Okay. Thank you. Very good afternoon to everyone. So I am going to speak about Earth, origin and evolution. When we say evolution, we have to begin with the origin of Earth and how it evolved over a period of time and how it is today. So we have to see the entire history of the planet. If you see, the Earth is the most active planet in the inner solar system, and is the largest planet also in the inner solar system. Here. And the activity inside this planet also caused the surface and the interior changes. That's what we see in terms of evolution. If you look at the smaller bodies like Moon, Mars, and Mercury, they are very small. because they're very small planets, they cooled very fastly and they become one plate planets. So because they became very inactive very long ago, they preserved the world heavily cratered surface like this. Therefore, the small planets contain evidences of geological processes that affected these planets about the first half of the solar system history. On the other hand, you look at the large planets like Earth and Venus, they are very different. They are active things for a long time because of the heat engine remains active. Therefore, they destroyed the world history. If we want to understand Earth, also Venus, we have to look at the Mars, Mercury, and Moon, look at their surface so that we understand the first 1 billion years of our own planet. The Earth is located here. It's the third planet from Sun, and it is placed between Venus and Mars. It is located in a habitable zone, such that the liquid water is present here, and also we have a suitable atmosphere, which helps for the development of life here. How does Earth form? So the Earth starts from planetesimals. This was explained yesterday by other speakers, how planetesimals forms from the solar system. So now to create Earth, we also need planetesimals. So when many planetesimals comes together and collide each other, they become bigger in size. They slowly grow in size like a planetary embryo or something like this. So ultimately, they grow to the maximum size. This becomes proto-Earth. So you start from planetesimals and you pass through the planetary embryo stage and you end up with proto-Earth. Because you had a lot of impacts of planetesimals also generated huge amount of heat. And also, Earth also contained short-lived radionuclides, the decay of which also produced lots of heat. So this heat melted the proto-Earth almost at the outer part of the proto-Earth is molten. So now whatever nickel and iron, these are very heavier elements, they settled in the interior part of the planet. They went to the core part of the planet and settled. So once you remove nickel and iron, the remaining part of the liquid is silicates. So that makes up the mantle and crustal part of the planet. So once you have this is called planetary differentiation, in which you separate core, mantle, and the crust. So this is happening just within 10 million years of time, less than 10 million years of time. So very quickly it happens. It also happens to the same way for Mercury, Moon, and also for Mars. So these stages are quite uniform between the planets. So once you have a proto-Earth, then what happens? The Earth also underwent a kind of giant impact. It is believed that a small planet like Mars-sized planets collided Earth about 4.5 billion years ago. So when that planet collided the Earth, huge amount of materials came out. Like here you see the small planet collides the Earth. Because of this collision impact, lots of material comes out, and the thrown out debris also goes around the Earth. And through different stages, they also produce a disk. So you produce a disk around the Earth, and some portion of the disk again go back to Earth and collide and accretes into the Earth. So whatever left out beyond the gravity field of the Earth, those materials form the Moon. So you produce Earth and the Moon. So now what happens to this primordial Earth? So now we want to understand the primordial Earth and how it evolved over a period of time. So when we want to understand Earth, we have to also understand various spheres like geosphere, hydrosphere, atmosphere, and biosphere. We are living in biosphere. We depend on atmosphere and also hydrosphere and geosphere. What happened? Biosphere, atmosphere, hydrosphere, all of them were produced from geosphere activity only. For example, the atmosphere comes out of geosphere through degassing process. So once you produce atmosphere, the condensation causes hydrosphere. Some of the water goes to the geosphere, they become groundwater. Then life also comes into pictures. So the evolution of geospheres significantly contributed to the evolution of all other spheres. So now let us look at the geosphere. The planet Earth, it has an interior. It has three important layers, as I already explained: crust, mantle, and core. The core mantle boundary is around at the depth of 2,900 kilometers. So now what happens? This entire, the three layers of this Earth is also very dynamic in nature. For example, the upper portion of the Earth is called the lithosphere. This is the rigid part of the upper shell of the planet, which is almost like a floating on asthenosphere, like wood floating on water. So the lithosphere is almost floating on asthenosphere, and it moves very easily on top of asthenosphere. And the lithosphere also broken into pieces, plates. So these plates also collide each other. Like here one plate collides onto the other plates, and one plate goes down the other plate. This is called subduction. So this is called plate tectonics. This plate tectonics is facilitated by the asthenosphere here. Otherwise, the plate cannot move on top of it, and the collision also takes place. So the subducted plate also goes down, and it's also going to the core mantle boundary also. So the circulation inside the planet causes a lot of activity, and they also causes the evolution of the planet. To see the interior of the planet, we have to use geophysics. Like for example, when there is an earthquake occurs on top of planets, the seismic waves goes through the planets, and they are reflected by different layers of the planets, and they are reflected back to the surface, and they are recorded. So the velocity at which these seismic waves are traveling inside are captured here. So you can see there is an increase in velocity of compressional waves, and when they reach the core mantle boundary, the velocity suddenly decreased because the outer core is liquid in nature. So this is how the geophysics help us to delineate the interior structure of the Earth. If you look at the temperature also increases from the surface. It goes up to 6,000 degrees centigrade. So all this information comes from geophysics. Now we want to understand the geological evolution of the planet. So how do we understand? If you want to understand myself, my body, I sample a drop of blood and study the DNA and various other biological parameters. Similarly, when I want to understand the planet, I need to sample the rocks. The rocks hold all the information. So if I want to answer the questions, how did Earth form and evolve to its present state? How do I answer? Then I have to go to this pile of rocks that are here. So here, the pile of rocks also should have ages ranging from the time of the origin of Earth to the present day, so that you sample the rocks belong to the entire history of the planet. This is very important. Second, the rocks also have three types. One is igneous rocks. The igneous rocks come from magma. So the igneous rocks tells about the magmatic processes that are happening inside the planet. On the other hand, if you study sedimentary rocks, they are forming from the water when it is reacting with the rocks. So it also erodes the rocks and carries the rocks along with the river, for example, river. So the sedimentary rocks are produced by the river, wind. There are many also ice. So these are all come from climatic processes. So atmospheric process, climate process, all of them are reflected in sedimentary rocks. So by studying the sediments, we understand the climate of Earth better. The third rock is metamorphic rocks. Both igneous and sedimentary rocks like these, they also buried inside the earth due to many tectonic activity. So when a sedimentary rocks buried goes inside 10 kilometers inside the earth, they also become metamorphic rocks. The changes as you go downward, pressure and temperature increases, through which the rocks also undergoes changes. Such rocks, when come to the surface again, we can look at them, study what happened at the depth of 10 kilometers. So this is how we understand the processes that took place in the earth, and we also need the age of the rocks. We have to determine the age of the rocks from the geochronological methods, which was explained yesterday, using isotopic records. So you have parent isotopes and daughter isotopes, the ratio of it, and also the half-life of these isotopes will tell us the age of the particular rock. So when you talk about the history of Earth, we should have a time scale. For example, the Earth born at the age of 4,500 million years ago. That's the origin of the Earth. And we need time scale from 4,500 million years to the present, 0. For example, 0. So the entire time scale is divided into 4 parts. The oldest one is Hadean eon. That span age from 4,500 million years to 4,000. Then comes Archean, it begins from 4,000 and ends at 2,500 million years ago. Proterozoic starts from 2,500, ends at 541 million years. Phanerozoic starts from 541 to the present day. Same way, we can also have time scale for Moon, Mars, and Venus. If you look at Moon and Mars, the pre-Nectarian periods, they're very equivalent to Hadean and Archean Earth. Similarly, the pre-Noachian and Noachian epoch of Mars is almost equivalent to Hadean. So we can compare the Hadean records of pre-Nectarian Moon and pre-Nectarian Moon of pre-Noachian Mars. Likewise, we can compare one planet to other planet. So this is the map shows the surface of the Earth containing ocean floor and the continents. This is where you find all the rocks. The continent contain all the old rocks starting from Archean, Proterozoic, and Paleozoic rocks. Whereas if we go to the ocean, this is very young. It's just formed in the last 100 million years. The Earth crust also broken into a number of plates, like ocean plate, continental plate. So those plates also what happened, they are breaking some places. For example, here it's called a divergent boundary. So they are break and open. Some places two plates collide. For example, ocean plate collides onto continental plate. Here you produce called subduction zone. And some places continent plate collides onto another continent, produce Himalaya. So this is the plate tectonic network of Earth. So what is the oldest rocks we have on Earth? This is the rock called Augusta gneiss. This is found in the northwestern part of Canada. A small piece, the scientists collect it and separate the minerals and study the isotopes composition of these minerals, which gave the age of 4 billion years. So this is the oldest rock we have. But you know that Earth formed about 4.5 billion years ago. So how do we know 4.5 billion years? This is come from the meteorites. Second, some scientists from Australia, they collected some samples from the southwestern Australia. This is the rock called conglomerates. So they powdered and separated a mineral called zircon. This is a very, very strong and highly resistive mineral. This gives the correct age of the origin of this particular mineral. They took this mineral and they determined the concentration of the radioactive isotopes, and they got the age of 4,400 million years. So here it is. They also found ages varying from 4,400 million years to 4,100 million years. This is the oldest minerals scientists discovered from Earth. Interestingly, when the scientists looked inside this mineral, they found some hydrous minerals are inside. When they studied, they found that it is a mineral called muscovite. The muscovite is a mica containing a lot of water. Therefore, when this mineral crystallized, there is lots of water was present at the time. Therefore, we can conclude that about 4,400 million years ago, water was present on Earth. This is another location on Earth in South Africa. There are also rock records also contain zircons like this. People separated and they dated. They got around 4,000 million years age for this type of zircons. Interestingly, these zircon minerals also contained some magnetic mineral inclusions. Look inside this grain, people found very few micron magnetite minerals. These magnetite minerals recorded the magnetic field that was present about 4.4 billion years ago. So they found the record that these magnetite minerals inside zircon also showed that Earth had a magnetic field at that time. Even there are other zircon grains also provided evidences that the magnetic field formed about 4.4 billion years ago, and it's almost continued up to 3,200 million years ago. This is very, very important finding because you need magnetic field to protect life on the Earth. You know how important it is. Even the rock records belong to the whole Earth history also preserve the magnetic field memory inside them. This shows that the magnetic field was there throughout the Earth history. So if you want to ask a question, when did magnetic field form? They formed about 4.4 billion years ago, and it is continuing to be active even today. This is very, very important finding that comes from the rock records. Therefore, whatever life produced in the last 4.5 billion years ago, all of them were preserved in the rock records. You look at Mars. Mars also had magnetic field, but today the global magnetic field disappeared. When did it disappear? About 4,100 million years ago, magnetic field disappeared from Mars. However, whatever rocks that were formed from 4.5 to 4.1 billion years, those rocks preserved the magnetic field that was present at the time. Some volcanoes on Mars also recorded the magnetic field that was present about 4.1 billion years ago. From this finding, we can say that volcanoes were active about 4.1 billion years ago on Mars. If so, on Earth also similar magmatism was there. We can infer. Anyway, Earth has lost all the first 500 million years of geological history. You know, we don't have Pleiadian geological record. We have to look at Mars and Moon. These planets preserve the geological record belong to the first 1 billion years of planetary history. If we look at this geological history, we can say that Earth also experienced huge amount of meteorite impacts in the first 500 billion years of time. Look at the surface of Moon and also Mars. You have huge amount of millions of billions of impact craters on the surface. Second, Moon also have an anorthositic crust. Anorthosite means it's a rock contains more calcium, aluminum silicate. These rocks requires magma ocean. Without magma ocean, these unearthed crates cannot be produced. Therefore, Moon and Mars had magma ocean. If so, did Earth also have magma ocean? Yes, some indications, some evidences are emerging. Look at on Moon, the magma ocean started about 4.48 billion years ago. This magma ocean, it's an ocean, but it's full of magma. It may be the whole moon is a magma ocean, or only the half of the moon was magma ocean. We don't know what is the real picture. We know that the magma ocean began its crystallization about 4.48 billion years ago. Once you have a magma ocean, from this magma, minerals also start crystallizing. The minerals that crystallize in the beginning, they are very heavy minerals like iron and magnesium silicates, like olivine and pyroxenes. These are very heavier minerals. Well, they are crystallizing at very high temperatures, and they are also heavy. They are heavier than the surrounding magma, so they go down. They settle on the floor of the magma ocean. Same time, another mineral called plagioclase also crystallizes from the magma, but these are all very light. These minerals goes to the top of the magma ocean, they form a crust like. So this is called anorthositic crust. So this entire anorthositic crust formation took place around 200 million years on the moon. We really don't know how much time it took on Mars and also on Earth. But we can now presently, scientists believe that magma ocean might have crystallized for a period of more than 200 million years on Earth also. Second, once the planet Earth is crystallized, they become solid on the surface, then whatever happens to the surface that can be preserved. For example, meteorite impacts. So there are hundreds of thousands of meteorite impacts happened on the surface of the moon, and they produced craters. Why do they happen? Just because of the main belt asteroids, which are sitting in between Mars and Jupiter. Yesterday you heard about planetary migrations. So when the planetary migration takes place, these asteroids present in the main belt will also be unstable. They also start moving towards the inner solar system. They go and hit Mars, Moon, Earth, and Mercury. They hit all the planets around 4,000 million years ago. This has happened. This also happened to Mercury. You look at the surface of Mercury, you have hundreds of impact craters, and the population density of these Mercurian craters are very similar to the moon. So the population of asteroids that produce craters on Mercury and those on moon, they are one and the same. And same thing also happened on Mars. Therefore, similar impacts should have also happened on Earth also. Therefore, the Marchi and others, they made a model that based on the records from Moon, Mars, and Mercury, they took all the crater population, they put it on the surface of Earth, theoretically, and they found that the entire Earth was covered by full of impact craters. So once the impact happens, it produces a lot of disturbances, it ejects lots of materials. All these materials cover the whole Earth. So about 4,000 million years ago, the whole Earth was covered by impact crater materials, like more similar to Moon. So this is how it is. Then slowly we are moving to Archean time, which is spanning from 4,000 to 2,500 million years ago. So this time of between 4,000 to 2,500 million years record, you only find in these red patches. These red patches are called Archean cratons. These cratons are also there in India, in South India, like Bangalore, you go to Karnataka, and some parts of Tamil Nadu, Orissa, also West Bengal. This area has lots of Archean crystal rocks that formed between 4,000 to 2,500 million years ago. These rocks give us a lot of idea about what happened to Earth in those time period. Yeah, look at this map. It tells you so many impact craters formed on the surface of the Earth. So far, we know about 200 craters formed on the surface of Earth, but you know there are several craters formed, but all of them are eroded. Only we have few tens of them. Some of them also formed during Archean time. So look at this graph shows the impact events over a period of time between 3,500 to 2,500 million years ago. There are many impact events also recorded. They are preserved in the rock records. For example, you go to the Western Australia Pilbara Craton, you look at the sedimentary rock record, people found a lot of impact craters materials are deposited in between several sedimentary rocks. These impact material craters, if you take and see, they have many impact spherules. These impact spherules are very diagnostic, very, very common if you look at impact crater materials. So from these spherules, we can say that impact occurred at that particular time. Then you talk about the continental crust. I still told you about continents. When did these continents form? They formed about 4,000 million years ago. Like rocks called tonallitic gneisses, granites, they all formed in different parts of the continents. Like, for example, Canada, Australia, you go to Indian Shield, also in North America, South America, all these areas, the continental crust is forming just because of magmatic events. The magma comes from the deep interior of the Earth. They come to the surface, and also they come to the crustal level. They produce a lot of a continental crust, something like this. And the granite is a very common rock which formed about 2,500 million years ago. You know, granites is commonly used in building material. We use for building and all. All these rocks formed about 2,500 million years ago in the continental crust. If you look at the Mercury planet, Mercury also got a lot of volcanism around Archean time. So look, there are the lava flows which are flowing like rivers on Mercury. So similar lava flows also may have flowed on the surface of Earth also. And look at Moon. Moon also have lots of long-lived volcanic activities in the near side of the Moon. Some of the lava flows formed about 3.6 to 7 billion years ago, and they also continue to present up to 1 billion years ago. Even look at Mars. Mars also had a lot of volcanic activity, like time in Archean on Earth. Volcanic activity on Mars is produced by mantle plumes. These are hot blobs coming, like they're coming from the core mantle boundary. They're originating from the core mantle boundary. They move up, they go and hit the lithosphere of Mars, and they are there for more than 4 billion years. They are continuously heating the lithosphere and produced a very largest volcano in our solar system called Tarsis volcano. And if you know the continents, the oldest continent that formed on Earth is called Walbara supercontinent. What is supercontinent? We know continent. If you bring many continents together, they become a bigger continent. We call it as supercontinent. One such a continent formed about between 3.6 to 2.7 billion years ago. Some parts of South Africa and some parts of the Western Australia, they came together and they produced a big supercontinent called Walbara. But you know, these supercontinent, they don't be stable. They will also be broken and open. They will be spreading out due to plate tectonics. Here are the rocks in the Indian Shield. In, for example, South India, North India, we have a lot of rocks belong to that particular time. And these rocks give us a lot about what happened to our own crust in the India. And we understood a lot about that. This is one of the oldest sedimentary rocks that we found on Earth, also in India. the Mazumdar and Chowdhury, they found this sedimentary sandstone from the Paleo-Archean rocks. This suggests that a river ocean was there about 3,500 million years ago in the Indian Ocean. Not only here, the whole globe. We have a lot of water. The ocean was there on Earth. Look at Mars. At about the same time, Mars also had liquid water on the surface of the planets. And it also flowed like rivers. You can see the river flows to the crater, impact crater, and it filled it. Did like a lake system. So this has happened around the same time on Mars. Same thing happened on Earth also. If you go to the Mars, you also see oceans. About 3,500 million years ago, ocean was there on the surface of Mars. And you have rivers, you have lakes, and Mars also have delta. Delta, you know, at the mouth of the river and sea, you find this delta. This is the delta on Mars. So Earth also had delta, like this type of delta sediments. So during the Archean time, we have atmosphere, but we didn't have oxygen. So there is no oxygen, but full of carbon dioxide and methane. But water was there, ocean was there. So life like today could not develop because of very poor oxygen level. But still, there are anoxic microorganism also grown at the time. 3.5 billion years ago, scientists found many microorganisms like microbial cyanobacteria. You can see some organic materials. These were discovered from the South Africa. So this suggests that some form of life, the microbial life, started about 3.5 billion years ago. At around the same time, the ocean was also there. Iron also there in the crust. The iron was leached out by weathering process. When water flowed, the iron was removed from the rocks. They went to ocean. In the ocean, cyanobacteria were there. They produce small amount of oxygen. When this oxygen was there, little amount, they reacted with the iron and they produced a deposits called banded iron formations. This banded iron formation was produced in the oceans of Archean time, and this became the biggest source of iron ore that we are extracting today. Whatever iron that we are using, they are coming from the banded iron formation, which formed in the ocean that exists about 3.5 billion years ago. Here is a mines in Karnataka. The Senthil mines is being mined by NMDC. So they exactly mining this type of banded iron formation. Not only that, if you come to the end of Archean, lots of collision happens. The crust are broken into pieces, they are colliding and diverging. So this was happening in South India also. And the plate tectonics was also operating, and there are plates going down and one plate going up. So lots of granites are produced because of this subduction process. So this is what we are seeing. So the granites are produced in South India, like near Bangalore. If you see Bangalore, you have find lots of granites. If you go to the Karnataka also, you find Hasan area, you find lots of granite. Hyderabad, you find lots of granites. So the granites are produced about 2,500 million years ago due to the plate tectonics process. Now we are going from Archean to Proterozoic time. So Proterozoic starts from 2,500 million years ago to 540 million years ago. So this is a very interesting time of Earth history. That's a time the atmosphere, the ocean, they produced oxygen. About 2.3 billion years ago, the ocean and the atmosphere produced a huge amount of oxygen. This is called a great oxidation event. Until then, there was no oxygen. There were very little amounts, but suddenly in the atmospheric oxygen went very high, almost very close to the present day, at least 1/10 of the present day oxygen level it reached. During this time, there are unicellular organisms started blooming in the oceans of Proterozoic Earth. These are some of the examples of fossils people recovered from the Proterozoic oceans. You find there are filamental fossils. These are all cyanobacteria. These are luckily preserved in rocks. And these are the organisms produce oxygen from the respiration. Also, during the Proterozoic time, you produced all the continents. Whatever continents are that you find today, most of them were produced at about 2,500 million years ago. These continents, they were not just keeping quiet. They are coming together like continental supercontinents, and they are breaking open and they are going away from each other. So this is called supercontinental cycles, which happened every 700 million years, 750 million years ago. One of the supercontinents formed between 2000 and 1500 million years ago. In Earth, this is called Columbia supercontinent. These continents subsequently broken. And once they are broken by plate tectonics, sometimes the mantle plume also coming from the interior of the Earth goes and hits the supercontinent, and they are broken into pieces. And due to the forces, they move away each other. So they are just almost dispersed. So these planets, the supercontinent is broken into pieces. They are moving away from each other. You look at the planet's position, the continental positions at 1,000 million years ago, and around 900 million years ago, again all the continents came together and assembled. This supercontinent is called Rodinia. This is not just story I'm telling. These are based on geological evidences that we get from the rocks. Again, this supercontinent Rodinia again underwent breakup. This breakup again opened up. Everything opened up, and around 780 million years ago, you can see the Rodinia is broken into two parts, and you can see the India is somewhere here. Then around 700 million years ago, the continental situations setup is something like that. And slowly they are spreading. And around 600 million years ago, there is something important happened to Earth that is called snowball Earth. This snowball, I will explain later. Then again, you see 600 million years ago, the continents are like this, 515 years. Most of them, some of them moved to the northern hemisphere. And finally, about 530 million years ago, you have the assembles of Gondwana lands. This is a very, very important continental landmass called Gondwana. Now, the whole Earth was covered by ice between 660 and 635 million years ago. The whole Earth was covered by ice. So the planet became cooler. So how do we get this type of situation? This is mainly because of the atmospheric gases. You know, carbon dioxide, methane, these are all greenhouse gases which heats up the atmosphere. So once you remove carbon dioxide and methane from atmosphere through some process, what will happen? The whole Earth become very cold. This is one situation. In the other situation, the sun is also evolving with time. And the sun was also not very powerful like today. So it was very light emitting, very less energy. So you have atmosphere and you have sun cycles also maybe playing a little role. And the whole planet was covered by ice. This is called snowball Earth, or you can say ice cream Earth. So now, this is what happened. The planet also became very quiet. The plates are not moving. Volcanoes are not erupting. You know, when the volcanoes erupt, it throws a lot of carbon dioxide into atmosphere. methane into atmosphere, sulfur dioxide. Then again they are coming to atmosphere, they will heat up the atmosphere again by greenhouse effects. So this is what happens subsequently. Again, the plates are start moving, and the ice are molten. Again, Earth came back to the previous position. Now the magic happened to Earth. This was about 530 million years ago. The ocean, you have nice ocean, you have Gondwana lands, and here, both on ocean and land, all life bloomed. Like, marine life blooms, and there's a lot of new life is coming, invertebrates are coming, trilobites, fish formed about 400 million years ago. They are preserved in rocks like fossils. So this is how the marine life is blooming, and even you find, a tortoise, and even you have whale. So all these lives are started blooming in the oceans. In the Gondwana supercontinent, you also develop land life, terrestrial life, like you have plant kingdom, and you also birds, and also reptiles, the dinosaurs. All these life forms are developing in the landmass of Gondwana. So this is a very most beautiful period of Earth history where all the life came into picture. But it's not a very simple story. This life also got interrupted by many mass extinction events. There are times where most of the life again killed by some extraterrestrial events or some volcanic eruptions. Lots of life again killed and dead. For example, end of about 4,450 million years ago, about 425, and there are 250 million years ago, 200 million years ago, and also 65 million years ago. Here, mass extinction occurred. That means almost 50% of the species were removed from Earth because this is called mass extinctions. This has happened several times. Now, scientists found around the same time, lots of volcanic eruptions also happened. For example, in Siberia, in the Russian area, you have huge amount of Siberian volcanism that coincide with these young Permian mass extinctions. Also, if you look at the 65 million years ago, you have very big impact event called Zixloop impact events that occurred in the Mexico country. Here you have an ocean and continents where a 17-kilometer diameter projectile meteorite came with a velocity of around 12 kilometers per second and hit the Earth's surface, and it produced a big crater like this. So this is around 170 kilometer size crater was produced by this meteorite impact. So what happened at the time? So from the crater, huge amount of material comes out, vapor plumes comes out, carbon dioxide, sulfur dioxide, all of them are removed. They are released to atmosphere because of huge amount of heating. At the time of impact, the temperature reaches of the order of 3000 degrees centigrade. The rocks are molten and they're vaporized and goes to the entire atmosphere of Earth. The whole atmosphere is present. Also, the dust particles covers the whole Earth. So the sunlight doesn't enters into atmosphere. It doesn't reach the surface. So no sunlight for months, no photosynthetic activity. So there is no life. Plants cannot grow. And global fire also happens. So this is the one particular impact is believed to have caused the removal of dinosaurs. For example, just imagine the impact itself disturbed the whole crust. Even you can see the effect of impact even at a depth of 40 kilometers. So this is the kind of, this type of impacts occurred on Earth in alien time. Millions of craters occurred. Even there are several craters occurred even later. So the impact events brings lots of catastrophe to the planets. Anyway, this is the Gondwana land that was there at about 500 million years ago. And this supercontinent cannot keep quiet. They also fight each other, it seems. They broke into pieces again due to some underlying activity, earth activity, like some kind of plumes. They comes and hits it, and they also break them into, again, number of plates. These plates also start moving away from each other. So this Gondwana land, Gondwana supercontinent, slowly became Pangea supercontinent about 200 million years ago. So this was the continental assembly, which was there about 200 million years ago. So now, again, this is hit by some mantle plume activity or several other processes. Again, these continents are broken into subcontinents. They also started moving from away from each other. And you look at our own Indians, this is the India about 60 million years ago. And they also started moving, going towards the Eurasian plates like this. So they were going like this and started rotated counterclockwise 30-degree. They collided onto Eurasian plate, and it produced a huge Himalaya. So this is how the India subcontinent moved and slowly collide onto the Eurasian plate, and it produced a huge mountain belt. In this process, the Indian lithosphere also gone beneath the Eurasian plate, subducted beneath. You can see here the right side, one plate gone down. This is Eurasian plate, this is Indian plates. So this is how the plate tectonics played a havoc to the planet Earth. So if you see plate tectonics, when it starts, this is around 2.5 billion years ago. Some scientists believe that it happened even before, but it was there in some form or other. But plate tectonics became very prominent in the last 2000 million years ago. This is how the plates are today. You are India here, and you have Asian plate, you have Russia, here you have African plate, North American plate, South American plate, Australian plates. These plates, even it is not quite now, this also start moving away from each other. We don't know, after 300 million years or 500 million years, again, there will be another supercontinent may be formed. Why not? So when these plates are moving across each other, they also produce lots of seismic activity. If you look at the earthquake map of Earth, you find that millions of thousands of events are occurring along the plate boundaries. This is mid-oceanic ridge. You can see the earthquakes themselves define the plate boundaries. You can see here. And this is Himalaya. That's where continent-continent collision occurred. So these are the chains of plates. You can see the swarming of lots of earthquakes. Look at our own India. You can see lots of, almost thousands of seismic activity. Earthquakes are happening all the time. And if we see, most of the earthquakes are occurring in the Himalayan region and also in the Andaman region. Why? Because that is where two plates collided just very recently. Recently means just 5-10 million years ago. They collided and still they are adjusting each other. They are hitting each other, produce large amount of earthquakes. Therefore, these regions are very hazardous to earthquakes. That's why, the earthquakes that occurred in the Nepal was devastated. Similarly, any part of Himalaya is very vulnerable to earthquakes. These activities are caused by faults. There are some weakness planes in the earth crust. They move up and down here and there. They produce lots of earthquake activity. Moon is also seismically active. The Apollo, when they went to Moon, they also installed 4 seismometer on the surface of Moon. they also recorded 28 moonquakes, which are very similar to earthquakes. But here, earthquakes don't show like plate boundary earthquakes that you see on Earth. Here, earthquakes are occurring very randomly. Earth also experiences many other type of earthquakes like deep moonquakes, artificial impacts, wherever you hit. For example, when Chandrayaan-3 landed on Earth, it should have generated some seismic activity. Even the meteoric bombardment also produced huge amount of seismic activity. Look at Mars. Mars is also seismically active. The NASA put a seismometer about 4 years ago on the surface of Mars, and it operated for about 4 years. So during this time, more than 1,300 Marsquakes were recorded by the seismometers, out of which some of them are very similar to the earthquakes that we occur on Earth. So these Marsquakes, you can see they're occurring along the active fault regions, but they don't show something like plate boundaries. So you don't have plate boundaries on Moon and Mars. Therefore, you don't have plate boundary earthquakes in these planets. Yes, now we come to today. The problem is global warming. You know, it's all come from carbon dioxide, carbon monoxide, sulfur dioxide. All of them are coming from the emissions from the vehicles, factories, and carbon dioxide content was about less than 300 parts per million around 1960. Now it increased to more than 400 ppm. So this addition of 100 ppm more carbon dioxide caused global warming. This global warming caused 1 degree, approximately 1 degree centigrade rise in global temperature, which caused melting of polar ice, and it also caused extreme weather. Like, sometimes you receive 30 centimeter rain in one day, like what happens in Chennai, Bangalore, also what happened recently in Dubai. So these things we never heard about 50 years ago or 160 years ago. So now we are start experiencing like a huge extreme events. All come from carbon dioxide. Now let me summarize the Earth history. Now you understood how Earth evolved from the beginning and how it evolved to the present day. During Hadean time, the Earth was just formed and the crust is very juvenile, very hot. Ocean just formed, atmosphere just formed, but there is no oxygen. Lots of meteorite impact occurred at the time. The magma ocean was there. From the magma ocean, crust was forming. Then it comes to Archean. The continents are start forming. Ocean is continuing to be there. Atmosphere was so full of carbon dioxide and methane. There are some micro life was there, and they are there here and there. Then when you come to Proterozoic, the supercontinents happened. Supercontinents are formed, broken. Many times they adjusted themselves. Ocean became very microbial life became more blooming to the intestine, and atmosphere also become more rich in oxygen around 2.3 billion years ago. And that oxygen remained in the atmosphere all the time. And if you look at the last 30 million years, the oxygen even become even more. So this is the very unique planet in which oxygen was blooming around the Proterozoic time. And life, the wide variety of life came into existence about 550 million years ago. The wide variety of life came into existence. But again, you have many mass extinctions that killed lots of life. So there was a great dying was there in Earth. So slowly you come to the plate tectonics, Gondwana land, break up. So again, Indian plate came and hit the Eurasian plate. India was produced, Himalayan belt was produced, and we have global warming now and many other things. If you look at Mars, Mars is not so like that. You look at and Mars, you have large amount of impacts were there in the beginning. Magnetic field was there only for 400 million years. Large impact, that heavy bombardment was there in the first 6-7 million years. Was there, volcanism was also there on Mars, but the quantity, the intensity decreased with the time. And Mars also had ocean. The rivers were active. They also flowing lots of water. But when you come to the recent time, all water gone. And this is how Mars. If you look at Moon, this was also not there. Just impact and impact, some volcanism, some tectonism, some. So this is how our inner planets and Earth is luckily very unique. That's why we are here to speak about it, to hear about it. So thank you very much.
Thank you, sir, for this wonderful presentation. We started with the origin and reached to the present state of Earth. So now we are ready to take any questions if they are there in the chat box. I request the participants to put their questions in the chat box.
I know you are very tired by hearing all the supercontinents.
Not like that, sir. We got few questions here. So first question is from Thokchom. What is the role of radon in determining seismic waves?
This is seismic waves. I think, I don't know, that's how it is related to seismic activity. Or evolution of planets, I don't know how this is related. I think this is something asked to some physicist. As a geologist, I store this question, I pass on to my physics colleagues. I'll get back to you. If you put your email address, I'll get back to you. Thank you.
Next question is from Atul Bikram. How did Mars lose its magnetic field?
You know, Mars is just half the size of Earth. And the inner heat also lost very early. So the smaller planets lose its first very rapidly by conduction. So the heat is a very, very important role that plays about the inner part of the dynamics of the interior. Second, this is what also causes the outer core, inner core activities. So somehow the mantle part of also become very, this is something arresting the dynamo activity, what I understand. But this is not a very well understood topic, why this is stopped something ago. But this is something to do with the thermal evolution of Mars, which scientists still trying to understand.
Thank you, sir. So the next question is from Anusri Majumdar. She's asking, as magma ocean is a critical stage in the tectonic development of rocky planets, what prevents the Earth from having magma ocean on its surface today, even though the temperature of interior of the Earth exceeds 4,000 Kelvin?
See, you know, Earth also has a lot of radioactive, long-lived radioactive isotopes. So they are also decaying with time. So you are removing radiogenic heat over a period of time. This is one factor. Second factor, once you open up plate tectonics, the young juvenile surface is coming out, they are exposed to surface and they start cooling very fastly. So this is not happening to one plate planet like Moon and Mars. There is no plate tectonics. Therefore, the whole outer shell of the planet is very intact. You can just break, fracture, but you cannot open them and move them away from each other like plate tectonics. So this did not happen to Earth. This is also partially due to the amount of water that was present in the mantle. So water also contributes to the viscosity of the mantle. So that also causes the mantle convection to effectively to occur in the inside Earth. So plate tectonics is the main answer, which causes also the heat thermal budget inside the water. Yep.
So the next question, I think, related to this, what we can address is why tectonic plates are displaced by
Yeah.
NISOM.
See why the plates are spread around. So you have to push them from the bottom. You have to hit it so that they go away from each other. So what hits it? It's a mega super plume, which is coming from the core mantle boundary. So they are coming to the bottom of the lithosphere and they hit it. While hitting it, they also uplifted, they are radially broken, they start moving away from each other. So another one is like mid-oceanic ridge situations, what you have today along the divergent boundaries. But here you don't have plumes. Here what happened, the asthenosphere upwelling is happening. So the asthenosphere decompressional melting takes place. But the supercontinental breakup, you need some bigger thermal source, something hitting from beneath, like plumes.
So next question is how life originated on Earth, although we found traces of bacteria millions years ago, but how they originated? This question is from Kavyasri.
That's a good question, but this is also not only your question, it's also my question. How did we get life here? Yes, there are two things possible. We look at Titan. Today, the Titan has a huge amount of methane ocean. You have methane atmosphere, methane is precipitate. So you have, and there are like amino acids are also synthesized in the atmosphere of Titan. So this is called a kind of prebiotic life. We really don't know whether Earth had similar kind of primordial life like methane ocean there on top of Earth. We don't have much information about it. But one thing, so this is something you start with the beginning. The second one is the comets. The cometary impact also brings a lot of primitive carbonaceous material. Whether that also supplied here, we have no idea. So the life evolution on Earth is certainly an intriguing question. But one thing, the magnetosphere was produced very long ago. So that was a very beautiful thing to happen to Earth. So that magnetosphere protected all of us, all the molecules, all the evolution can take place in the biosphere. Yeah.
So I think we can end up with this question as instructed by Dr. Praveen Kumar. Thank you, sir. Over to you, Praveen, sir.
Yeah. Thank you, Dr. Senthil Kumar, for this wonderful talk. And you have taken us to billions of years back, how our Earth originated and evolved over the time. Very informative and educative lecture. Thank you, Dr. Senthil. And also, I would like to thank Mr. Abhishek for nicely moderating the session. Thank you, both of you. And to all the participants, we will have the next session on.
Bye.
Yeah, we will have the next session on Monday, which will have 2 lectures. And by the same time, we will meet. That is at 3:30. Meet you all on Monday, and have a very nice weekend. Thank you all.